Alright, so this is 4.2 mean value theorem. It has a little Rolle's theorem in there as well. So first I want to point your attention to Rolle's theorem, this one here. It says if f is continuous, it has some conditions. So the function has to be continuous on a particular interval, ab. It has to be differentiable, so you have to be able to find the derivative everywhere on the whole interval. And for Rolle's theorem, when you plug in the endpoints, they have to equal the same y value. If all of those things are true, then Rolle's theorem says that there has to be a c value or an x value. A c is just an x value. So there has to be a c value in the interval such that when you find the derivative at that particular spot, that the derivative actually equals 0. So that's Rolle's theorem. We'll do an example of that. And then mean value theorem, I just want to get the theorems down and then I'll probably erase them. The mean value theorem, that says that it's very similar. It says that if f is continuous and differentiable on the same interval, ab, then there exists a c, so again an x value, such that when you find the derivative at that spot, it equals f of b minus f of a divided by b minus a. And what that means is actually this is the slope of the tangent line. It equals the slope of the secant line connecting the two endpoints. So again, we'll definitely take a look at a couple of examples. So let me do example 1 here. Alright, so let's say we want to find all the c's. Find all the c's that satisfy Rolle's theorem. Okay, so we'll give you a function. So f of x equals x cubed minus 3x squared plus 2x plus 5. And then what we're going to have to do, and they'll give you an interval. So let's say, hey, the interval is from, this one is from 0 to 2. Alright, so then the first thing you'll do is you can check to make sure that it satisfies the hypothesis. So first you have to check, is this really a continuous function? Well, it's a polynomial, so any polynomial is going to be a continuous function. So check, it is continuous. Is it differentiable everywhere? You know, are there any issues where you think, oh, I couldn't find the derivative at certain spots? Don't see any issues there. Are the endpoints the same? Like, so when I plug in f of 0, does it equal the exact same value as when I plug in f of 2? Not sure, we'll have to check that out. So f of 0, you can tell if you put 0 in these spots that you get 5. I'm sure you guys can figure out if you plugged in a 2 there. That would be, I don't want to do all the work, but maybe I do. So 2 cubed minus 3 times 2 squared plus 2 times 2 plus 5. I believe that will also, that'll give 8 minus 12 plus 4 plus 5. Yeah, negative 4 plus 4, so the endpoints, they give you the same y values, okay? So Rolle's theorem says that there must be a spot where the derivative equals the same as the slope connecting the two endpoints. So what we would do is we need to find the derivative. So we have f prime of x, and we say that equals 3x squared, we know derivative of this, and then minus 6x, and then plus 2. So there's the derivative. And we're going to set that equal to 0. So for Rolle's theorem, we always set it equal to 0. Because that's what it would be if you were to, well, you'll see, we'll just always set it equal to 0. So we say equals 0. And then we would have to use the quadratic formula. So I'm going to actually assume you guys know how to do the quad formula, and we should get a couple answers. We get 3 plus and minus square root of 3. Now the only answer we would care about for this, this would be x equals, the only answer we'd care about are the answers that are actually on the interval from 0 to 2. So we have to kind of mess around there and figure out, which of those numbers would that be. 3 plus radical 3 would be too big, so we would pick x equals 3 minus radical 3. Now, what is it exactly that we found? Okay, this is the answer. This is the c that we're looking for, if you will. I don't use the c, I actually just go ahead and look for the x value that we're trying to find. But this is what we found, the c. Alright, so graphically, here's what we just found. We have a portion of the graph, 0, 5, we're talking about from 0 to 2. So we go 0, we plug in a 0, we get a 2, and when you plug in a 2, I'm just kidding, when you plug in a 0 you get 5. That's what we discovered. So you plug in a 0 you get 5, so 0, 5, and then when you plug in a 2 you also get 5. Okay? 2, 5. Now, in between there, the graph kind of goes like, let's see, graph kind of does this a little bit. Let's see, maybe something like that. And what we're saying is that there is a spot on the graph where the slope of the tangent line equals the slope of the line that connects those 2 points, which we call the secant line. So right here, this actually has a slope of the tangent line there of 0, which is the same as the slope of the line that connects these 2 points. This is also 0, the slope there, and it's the same as where it occurs here. 3 minus radical 3, how big is that? That's about 1.26. So if I drew it a little bit better, it actually would be like about right here, like 1.26. Okay? So this is where this graph levels out. So we're saying the slope at that spot equals the same as the slope that connects the 2 endpoints. That's what Rolle's theorem says. That's what the mean value theorem says too. It's just that the mean value theorem doesn't need the endpoints to be the same. They don't have to be level like this. The mean value theorem's a little bit more, let's say a little bit more powerful than Rolle's theorem. Alright, let me erase a little bit. Okay, let me do a mean value theorem problem. Okay, so we have function f of x equals x squared plus 2x minus 1, and they give us the interval 0 to 1. So what we need to do is we need to see if it satisfies even the hypothesis. And the hypothesis for the mean value theorem is that it has to be continuous. So we look at it and we're like, okay, it's a polynomial, it's a parabola, so it's going to be continuous. So it's continuous. And is it differentiable everywhere? Does it have any issues or anything? So no, we're going to say it's fine, so it's differentiable everywhere. Okay. So then what we need to do is we just need to find the derivative. So we're going to say f prime of x. Derivative would be 2x plus 2. What you're always going to do is you're going to set your derivative. So here's the mean value theorem again. The derivative equals f of b minus f of a over b minus a. Now the a and the b are the endpoints of the interval. So what you'll do is you'll take your derivative, so that will be 2x plus 2. You'll set it equal to, and these are y coordinates. These are the y coordinates that you get when you plug these in. So what we're saying is we need to figure out what f of 1 is minus f of 0 and then we're going to divide that by 1 minus 0. So we have 2x plus 2 equals, and then we have to plug a 1 in there and see what we get. So f of 1, I did that a second ago, and I got 2. So I plugged a 1 in for this, and I got 2. Then I figured out f of 0, so you can tell if you plug it in, you get negative 1. So 2 minus negative 1, all over 1 minus 0, which is 1. So we get 2x plus 2 equals, it looks like 3. So we have 2x equals 1. So I need to make sure this shows up. So I would say that x equals 1/2. Now, what did we find out? We found out that the c that we were looking for, or the x that we're looking for, is 1/2. So graphically, let me show you what we just found out. So we're talking about the interval from 0 to 1, and this is just kind of a portion of a parabola. So 0, let's see, we said it was 0, negative 1, so right here, 0, negative 1, and then our other endpoint was 1, what do we say, 1, 2, so 1, 2, right here. So again, it's just kind of part of a parabola. We're saying that there is a spot on that interval that has a slope that's exactly the same as the slope that connects the two endpoints. So this slope right here, that's the slope of the secant line. And then we have a spot on the curve, we're saying that it's at 1/2. So right here at 1/2, we're saying that that slope is exactly the same as the slope of the secant line. And that's what the mean value theorem says. It says there is a spot where the slope of the tangent line, equals the same as the slope of the secant line. Okay, so that's really the gist of the lesson. And let me see if there's anything else. There are some really good applications about this. I'll give you one. There's a really good toll booth application. Okay, back east, they have those toll booths where you go through and you pay a fee, and then you go, a little while longer, and you pay another fee for the next one. Well, let's say that a trucker goes on a toll booth, and he, let's say he starts off here, 0, 0, okay, and then he goes through a toll booth, and then 2 hours later he goes to another toll booth, and they give him a ticket. They give him a speeding ticket just right when he goes through. He's like, what are you talking about? And they say, well, we know you were speeding because you went from here to here in this amount of time, and that's more than the speed limit, and so we're going to give you a speeding ticket. And he's like, what? How do you know I was even speeding? Well, here's how they can kind of figure it out. So they know that in 2 hours, let's say he covered 159 miles. There were 159 miles separating the toll booths. So in 2 hours, he was able to cover that distance. Who knows how he did it? His graph might look something like this, okay? They hand him the ticket because they know that his average speed, if they were to figure out his average speed, they would say, okay, he went, you guys know your basic distance equals rate times time. So d equals rt, so if they wanted to figure out his rate, they would just take his distance, which is 159 miles, and they would divide it by the time, which would be 2 hours, these are hours, and that means that his average speed was 79.5. Well, the speed limit, let's say, is only 65, so let's say 65 miles per hour. So they know he was speeding, because his average speed was 79.5. Well, his average speed is the slope of the secant line. Because if I connected these dots, this dot right here is 2, 159, and this one is 0, 0. So that's exactly what this is. The slope of the secant line, it's 159 minus 0, and 2 minus 0, and that's where you get your 79.5. Well, there has to be some spot on here where the slope of the tangent line equals the same as that, and that right there would be his instantaneous velocity. So they know at some point he must have actually been going 79.5. So according to this graph, this would be the spot right here where he was actually going that exact same speed. So instantaneous velocity, this remember the slope of the secant line is average velocity. So it's a good application. So I think that will help a little bit doing some of the problems. Okay.